Dear students, let us now see the next property of the Fourier transform, that is the time reversal property. If the Fourier transform of x of t is x of omega, then Fourier transform of x of minus t is x of minus omega. So we all know that the time reversed form of a signal is nothing but x of minus t. So if we are taking the Fourier transform of x of minus t, then we will be obtaining x of minus omega. Now let us see the proof. By definition, the Fourier transform of x of minus t will be what? Integral minus infinity to infinity x of minus t e raised to minus j omega t into dt. Now here we can replace minus t in the RHS by t. Okay, minus t has been replaced by t. So Fourier transform of x of minus t is equal to integral minus infinity to infinity x of t e raised to j omega t dt. Minus t has been replaced by t here. In such a situation, there will be a change in the limit of integration, but here our limit of integration is from minus infinity to infinity, the entire range of t. Then that is why it is having no change at all. The limit of integration has no change. So let us see here. Now x of integral minus infinity to infinity x of t raised to j omega t dt. So that can be replaced in this way, that can be changed in this way, e raised to minus j into minus omega into t. Okay, e raised to minus j into minus omega into t. Now if we compare it with the definition of Fourier transform, this will be equal to what? X of minus omega, because e raised to minus j into minus omega into t will be x of minus omega. So the Fourier transform of x of minus t, the time reversal signal is x of minus omega, Now let us see the next property of the Fourier transform, and that is differentiation in time domain property. When the Fourier transform of x of t is given by x of omega, then the Fourier transform of d by dt of x of t is j omega x of omega. So here we are considering or taking the differentiation property or the derivative of x of t. Okay, here we are considering the derivative of x of t, that is d by dt of x of t. That is, in fact, when we are taking the Fourier transform, we will be getting j omega x of omega. Now let us consider the proof of the given property. Now here let us consider the equation of the inverse Fourier transform. X of t is equal to 1 by 2 pi integral minus infinity to infinity x of omega e raised to j omega t d omega. That is the equation of the inverse Fourier transform. Now here we can differentiate both sides with respect to t. Differentiating both sides with respect to t. So what we're getting here is in the left hand side LHS, we will be having d by dt of x of t. Okay, in the LHS we are having d by dt of x of t. In the RHS right hand side, 1 by 2 pi is a constant that is taken outside here. D by dt of integral of x of omega e raised to j omega t into d omega. Here again we are differentiating it with respect to t. So that is why the differentiation is applied only to the function which contains a variable t. So that is here e raised to j omega t. So differentiation is applied only to this function, that is e raised to j omega t. So we are only taking the derivative of e raised to j omega t in the right hand side. So what is the derivative of e raised to j omega t? D by dt of e raised to j omega t is nothing but j omega into e raised to j omega t. So that is equal to j omega into e raised to j omega t. So we all know that the derivative d by dt of e raised to e power ax will be equal to a into e raised to ax. E raised to ax into a. So that is what happens here. D by dt of e raised to j omega t will be equal to j omega into e raised to j omega t. So this j omega is again a constant that is taken outside. So j omega goes to the outside, and what the remaining terms we can club it together. That is 1 by 2 pi integral minus infinity to infinity x of omega e raised to j omega t d omega is nothing but what? That is inverse Fourier transform of x of omega. That is as per the definition. That is the equation for the inverse Fourier transform of x of omega. We can see, so it is here expressed as a j omega into Fourier inverse of x of omega. Okay, so this equation is again the inverse Fourier transform of x of omega. So that is expressed as f inverse of x of omega. So now we can see that the Fourier transform of, once again we have to consider take the Fourier transform on both sides of this expression. In the left hand side we have to take the Fourier transform of d by dt of x of t. So that is the left hand side Fourier transform d by dt of x of t. So when it comes to the right hand side, we have the term is j omega Fourier inverse of x of omega. So we have to consider the Fourier transform of this function, that is equal to j omega is a constant that is taken outside. Then we are considering the Fourier transform of inverse Fourier transform of x of omega. Okay, that will be equal to what? That will be equal to x of omega. So there is an inverse Fourier transform. Once again we are taking the Fourier transform, we will get the original function. Okay, so we have let us see it. If the Fourier transform of x of t, we all know that is equal to x of omega, then the inverse Fourier transform of x of t is what? X of omega is x of t. So again we are taking the Fourier transform of the inverse of x of omega, or the Fourier transform of that is equivalent to Fourier transform of x of t itself. You see, Fourier transform of f inverse of x of omega. F inverse of x of omega is nothing but x of t. So Fourier transform of x of t is again that will be equal to x of omega. Okay. So j omega x of omega. So we can see the final answer will be, the result will be Fourier transform of d by dt of x of t is j omega x of omega. This equation can be extended to any powers of differentiation. That means if you consider d raised to n dt raised to n of x of t, then its Fourier transform will be equal to j omega raised to n x of omega. So nth power or nth order differentiation, d raised to n into d raised to n divided by dt raised to n of x of t, its Fourier transform will be j omega raised to n x of omega. So that is the differentiation in time domain property of the Fourier transform. Thank you.